Alright, we're going to get started. Homework, last chance. Okay, if you haven't turned it in here, I hope it's either in my mailbox or by the door. Alright, so last time we talked about isothermal reactor design, right? And really we were talking about CSTRs, is where we spent most of the class. So today we're going to switch it up to PFRs, tube reactors. And so let's start with the system at constant temperature and now not constant volume like we had last class because it was liquid phase reactions, but constant pressure. Okay? And we're just going to consider some generic reaction. A goes to product, and the rate law is given, and we're going to make it a squared rate law this time instead of the normal linear rate law. Alright, so we draw a little diagram. We've got a flow rate of A coming into the unit, flow rate of A leaving the unit, and some specified conversion. And as you might have guessed, the goal is to figure out how large does the reactor need to be in order to hit some specified conversion or vice versa. Yes?
So, one thing I've been thinking about, when you say size or volume in terms of a PFR,
Sure.
how do you, like, is there a relation for, like, cross-sectional area, or?
So, I mean, what's the volume of a cylinder?
Right, so,
Right? Area times length.
more in terms of length, or?
Oh, okay, so I mean, that's a good question. So if we were designing these systems, I think is really what you're asking. Would we be looking for our tube of a certain length or a certain area? What do you guys think? That's what it comes down to. Imagine that I have it and I want to make the cross-sectional area really, really, really big. Can you imagine that you might start running into trouble where it's not going to act like a plug flow reactor anymore, right? So your area is usually constrained not necessarily by how much conversion you want, but things like mass transport, heat transport, and pressure drop. Okay, so those are the things that will put bounds on your area. So if my area is bounded, then what else can I change in order to make the volume? The length. Okay? So that is a good question that most of the time, and a lot of the homework questions are phrased this way, you're asked about a length of a PFR rather than just the volume, because the area, again, is fairly constrained by other matters. Not ones that we'll neglect in the class, but ones we're not going to talk about yet. Okay, but yeah, we've got some set volume. And so where do we start? You guys remember the 6 boxes we put up on the board yesterday, or Tuesday? Right. So also known as the design equation, right? And so we can write FA naught times the change in conversion, the change in volume, is equal to the rate. What was number 2? Heard somebody say it. Rate law, yeah. I like putting rate equation because laws are things you can break. Alright, I gave you that, so that's very simple for this case. You don't have to worry about deriving mechanism. What was the third thing? Stoichiometry. Can we do that in this case? No, I'll put it up here anyways as a reminder. We're going to work an example in a second where we'll worry about this, but for now, I'll just say, make the table. So we are going to put the resulting formula up here, but we're just not going to make the whole table because we don't know what products we're making. Okay. So at constant temperature and pressure, what's changing? Nothing's changing in time, right? Because I'm at steady state. But what has to change versus for this flow versus this flow? Oh, sure, the conversion. But if I'm at constant pressure, what changes? Volume, right? Volumetric flow rate in this case, don't get it confused with the volume of your PFR. But your volumetric flow rate will change, and that's because you're at constant pressure. Now, that's only true if you have a reaction like A goes to 2B, or A goes to 1/2 B, something like that, right? So it's only true when that epsilon parameter is not equal to 0. But just remember it anyways, because if epsilon's 0, the equations just simplify. And so we can write out the equation, concentration of A, the flow rate of A over now not the volume, but the volumetric flow rate. And I can't put the 0 here again because it's changing. And so I'm not going to rederive it because we did it a couple class periods ago when we were talking about stoichiometry. What you end up with is FAO, 1 minus the conversion, over the initial volumetric flow rate, or the inlet volumetric flow rate, 1 plus epsilon x. And this grouping of terms is simply the initial concentration Yeah.
Just to make sure, this is a gas phase reaction?
Yes.
Okay.
So yeah, this is the one to remember, and then if epsilon is 0, then it's just, this simplifies, right? That just means that you don't actually have any change in volume because you're not, as the reaction proceeds, you're not removing moles of gas from, you're not removing or adding moles of gas from the big. Okay, so we can combine that with the rate law. And with the design equation. And so you get FAO all of this squared. Why? Why is all this squared here? Right, because of the rate law, right? Because it's a second order rate law. Notice though, does this equation right here depend on the rate law? No. Okay, so don't let it throw you. It's the same equation that we were dealing with yesterday. This doesn't depend on the rate law. It depends on things like whether or not there's volume change, whether or not it's isothermal, whether or not it's gas or liquid. All that stuff matters. But the rate law is not in here. That's just in this step 2. So you can kind of see how things are compartmentalized in order to help you, right? You can do the stoichiometry without knowing anything about the rate law. Just like when we started, we could solve for the rate law from a mechanism without knowing anything about all these flows and concentrations and stuff. It's only when you combine them that now suddenly things depend on both the rate law as well as the stoichiometry. All right, so the last step is what? Integrate, yeah. Everybody knows that integral, right? Off top of their heads? You guys can just, no? No Goodwill Huntings in here or anything? Yeah, I don't either. There's an integration table in the back of the book. I think it's like Appendix 1. That can help. To actually solve this integral, you use integration by parts. Today, I'm just going to write it on the board. How about that? So the volume is equal to FAO.
Isn't the volume squared as well?
Yeah. Thanks. And you get this. notice that this is my volumetric flow rate at the inlet. So one of the CA knots has disappeared, but the other one is still there. Right? Everybody see that? Because V naught is simply, okay? So I'm just substituting that in at the same time. Obviously this keeps going. All right, everybody got that? Okay, so if I give you a conversion, can you tell me a volume? Is there anything stopping you? Right? Speak up. Epsilon, right, but obviously I'll have to tell you the stoichiometry of the reaction that you're dealing with. And you'll have to be given the volumetric flow rate at the inlet, or given the things that you need in order to compute that, but that's not a problem. And so yeah, you can solve this, but now what if I do the opposite? What if I give you a volume and I ask for the conversion? How would you solve that? Computer. Yeah, that's right. You have to solve it iteratively. We won't be doing guess and checks on the test or anything like that. But no, set up a little Excel spreadsheet and use Excel Solver, and it'd be pretty quick. All right, so let's plot what this looks like. And we had the question, it was a little too early. I'm actually going to plot versus length. And again, this is because that's the more important parameter when we're talking about a PFR. So if I plot conversion, so I'm bounded 0 to 1, and then some length, and you get a curve that looks like that. And that is for epsilon equals 0, which is the same as me saying A goes to B. Right? Yeah?
So, do we have ever a complex epsilon that feels like partial molar volumes or anything like that?
No.
And, okay. So we just go assume epsilon based off of stoichiometry and assume everything has the same density?
I mean, epsilon's defined based off of stoichiometry. If you had the types of things you were talking about, you'd have to rederive the equation. Does that make sense? You'd have to go all the way back to where we used epsilon so that we could reflect that. But you're going to be dealing with ideal gases, ideal liquids. Now, we are going to talk about reactions with phase change. I don't know if we'll get to that today, but we might. So that is something that you have to worry about. But otherwise, you're not going to have to worry about things like, species having different densities. These are ideal gases. Yeah.
Does this relate to like boundary layer thickness from like transport classes? Like
The shape?
Yeah.
It may, but I would guess not. I'd have to look back at the integral, the pre-integrated form to see if the shape is similar. But you get a lot of shapes like this and go up and level off. All right, what happens if I go to a positive epsilon? Is the curve going to be lower or higher? So break it down. Given a fixed volume, would I expect, so let's say I've got some volume, there's my conversion for A goes to B. Now everything else is the same, but now I'm considering A goes to 2B. Would you guys expect the conversion to go up or down? All right, good. You got some ups and downs. It's going to go down. Why? Somebody who said up. Were you guessing or do you know? You were guessing? So what two things happen, right? As we go to 2B, what's happening? We are generating moles, which means what happens to the volume? And what type of volume? We're not talking about the volume of the PBR, the PSR doesn't change. the volumetric flow rate increases. So what does that do? Why does that decrease conversion? It decreases residence time. That's explanation number one. I'll put that one on the board. There's another one. Sorry, that's not the initial, that's the actual volumetric flow rate. I know this sounds cyclical, so hopefully it's not confusing you guys. But as the reaction proceeds, the volumetric flow rate increases, right? But only if epsilon is greater than 0. And as the volumetric flow rate increases, the residence time decreases, which decreases your conversion. So you would get lower conversion if epsilon was equal to 1. This one's probably easier to guess, right? If I have A goes to 1/2 of B, epsilon is equal to minus 1/2, the conversion would be higher. What's the other reason?
Concentration of A goes down.
The concentration of A goes down, yeah. Same reason, or no, different reason this time. As I'm making B, right, more B for A goes to 2B versus A goes to B. With a given conversion, I'm making more B. More B means the concentration of A drops. Now, of course, it's dropping either way because you're consuming it. But it's dropping more rapidly if epsilon is greater than 0. So yeah, and of course, if the concentration drops, rates depend on the concentration of my reactants, so it also drops. So it's a mixture of both reasons, but this is the shape that you get. And of course, you can continue this, right? It just keeps going down. Does that make sense? Yeah.
Is that a general rule for all equations that you can kind of keep in your head, or is that?
I mean, I can write a rate equation where the rate's inversely proportional to reactants, sure. So it wouldn't work there. This is, yes, I mean, that's a good question. What is this specific to? This is specific to the rate equation we started with. It would look differently if I had just a normal linear rate equation, but it wouldn't look that differently. This concentration term, which I've erased, would go away, but and these, you know, the integral would be totally different. But you'd have similar behavior in that as you increase epsilon, you decrease conversion given a fixed volume. Okay, it's kind of a silly thing because, of course, we can't actually change epsilon. We have no control over the chemistry. Yeah.
Can you go over that first statement again about if concentration or conversion increases, the flow rate increases, and then that second part, I'm not understanding, is flow rate increases.
So just think about it, right? As I'm doing the reaction, I'm making more moles of gas. So the flow rate's got to speed up, the volumetric flow rate. You're with me so far?
Yeah.
Okay, so if I'm going faster through the reactor, I'm spending less time in the reactor. So I'm going to do less reaction. That's it.
So conversion is going up.
I know, I think this is the confusing part, but this is saying that the conversion would go down in a given amount of space. If I were somehow able to change epsilon from 0 to 1. Again, you can't actually do that, but it's important to understand, to have a gut reaction to how epsilon should be changing the different things that you're dealing with. Okay. So let's look at a specific example so we can put numbers on the board and we're not dealing with something as vague as A goes to products. that? Speak up. Can't hear anybody. Not an ether. It's a chemical.
Propionate?
It's a peroxide. That's what the two oxygens in the middle mean. So you have oxygen, oxygen. And what's this thing at the end? Tert-butyl. This is ditert-butyl peroxide. Are peroxides very stable? No. So this is a gas phase reaction that's real that you don't need catalyst to carry out. You just heat it up. And it degrades into, what's that? What's that? What's the CO in the middle tell you? Ketone. So dimethyl ketone. Anybody know what dimethyl ketone is? Acetone. Yeah. Okay. Let's not forget that we're chemical engineers. Just occasionally. And now I'm going to do you the favor and throw away the chemistry. Yeah. Don't forget your stoichiometry, though. All right, and we're going to do this, as you might have guessed, in a PFR. Constant temperature of 400 Kelvin. Constant pressure, 10 atmospheres. And as I just said, pressure drop, effectively 0. And FAO, the feed into the PFR of your reactant, is 2.5 moles per minute. All right. What's the first step? Mole balance, aka design equation. What's the second step? Rate equation. Did I give it to you? You guys are experts at chemistry, right? What do you guys think this might be? It's a unimolecular reaction, and we talked earlier in the class about, and under most conditions, unimolecular reactions they simplify into first order rate law. Okay, so negative RA, K times C. Again, a lot of the time you'll be given that, unless I'm testing you on your ability to derive a rate law from a mechanism, which is probably something that I should test you on. All right, stoichiometry. This time we'll actually draw the table because we have a reaction. Do we have any inerts? No. Do you usually have inerts? Yes. All right. FA naught. I don't have any flow of B or C coming in. So what is FT naught equal to? Just FA naught. Yeah. Pure feed. Okay. The change, I'll just put delta today. Minus FAO times X, right? I don't have to worry about dividing through by a stoichiometric coefficient. I don't have to worry about which reactant is limiting. Unimolecular. It's written with a stoichiometric coefficient of 1 on the reagent. So it's just that. And then FAO times X, because that stoichiometry is also 1 on B. But here I've got to put 2 times FAO times X. Yeah, like a yard sale up here. What a crap. Any questions? Good. All right. Are we done with stoichiometry? No. What's the goal of stoichiometry?
To put it somewhere else.
So what?
Take what you know and put it somewhere else.
One, concentrations of species as a concentration of conversion. We're not there yet. Ca is equal to Fa divided by the volumetric flow rate. Is the volumetric flow rate constant? No. Epsilon is 2, right? I'm making 2 moles of gas every time I do the reaction. Okay, so that's not constant. Because we're at constant pressure, so something's got to give. So now we have Fa naught, same equation that we had earlier. Yep. All right, what's the fourth step? This is really what you're saying. Take what you know, put it somewhere else.
Yeah.
Right? Now you want to combine steps 1, 2, and 3. Okay, so we write out Fa naught dx dv equal to K times Ca, which is this whole expression, so we get Ca naught 1 minus x, 1 plus epsilon x. So you can compare this to the one that you had in your notes earlier. That's the difference between a second order rate law and a first order rate law, right? This is not squared anymore. These 3 things would be squared. Otherwise, it would be the same. Of course, that changes everything from here on out because next thing we're going to do is integrate this. And again, via magic, do you guys think that you're going to have to do any integration on a test? You will be given an integration table. Remember that you will have notes. So if you want to write down the integrated form for first order, second order, zero order, that's maybe a good idea, but you might not get a first order, a second order, or a zero order rate. So what do? Know how to use an integration table. You will be provided one. Know how to use it. Okay. All right, 6, evaluate. So notice that nothing that we've done so far has required any numbers or anything, right? This is just following a recipe, and now we're actually going to solve the problem. Okay, V naught. What's that equal to? Not FAO, but let's think generally. Which flow? Flow of A or total flow? Total flow. Yeah, in this case it's the same, but let's, think generally. And then the total concentration. Remember, that's just the definition of concentration rewritten, right? We've been putting this on the board 4 times a class. So this shouldn't throw you off. All right, what's the total concentration of species? You will not be given it. You've been given everything you're going to be given for this problem. Huh?
Oh, no, for gas.
It's a gas. So what do I use?
Why?
Ideal gas law. Right? Because concentration right? PV equals nRT. Alright, so let's actually solve that out. What was the pressure I told you guys earlier? Again, don't be as cavalier as I am with your units. So we convert 10 atmospheres into pascals, and then we can put in the rest. And so we get, for the concentration, 0.305 moles per decimeter cubed. Never seen a book or a set of notes so in love with decimeters. Coming back to here, right? What's the total flow rate coming into the unit? We had it up earlier. It's at the bottom of your stoichiometry table. It's equal to FA naught. And that I gave you is, what was it, 2.5?
Yeah.
Moles per minute?
Yeah.
Okay. Alright, what else were we given? What else do we need? What else is in here? K. Alright, what was K? Did I give you guys K? That's the trick in the problem, and then I left it out of the problem statement. That's right. Alright. What temperature are we at? 400 Kelvin. What's that in Celsius? 127. What did I say, minus 27? 127. So not 50. So what do we do? Hmm? You're fine. Serious. So remember, K is equal to some pre-exponential constant. A lot of times that's written as A. Sometimes you'll see K naught times E negative EA over RT. So how do I use that to get the rate constant? Hmm? Yeah, I mean, there's a few ways to do it, right? You can solve for K naught and then substitute that into the equation. Or you can use this form, which simply tells you K at T2 is equal to K at T1 So that's a nice equation to know. It just saves you some time. This is not K times T2. Okay.
just take the ratio of the two, basically?
Yeah, I mean, there's at least